We figured out what the fourth order Lagrange polynomial was to represent the Bessel function in our previous video. And now what we're going to do is we're going to perform the rest of the problem where we actually analyze the accuracy of the Lagrange fourth order polynomial. And so we're going to approximate at the Bessel function at 1.9, 2.1, 2.3, and 2.5. Then we're going to go ahead and compare the actual values to the predicted values in a table, find the percent error. And then finally, we're just going to plot the predicted points on the actual Bessel function to see whether or not it makes any sense or not. And of course, the closer those interpolated points are to the line, the better the prediction, which means that the polynomial model that we created seems like it'll be a good one. All right, so this is what we did last time. And now let's go ahead and print out what the predicted values are. And remember, we haven't even seen whether or not the polynomial is actually even close to the Bessel function at the points given. All right, so let's see what we get. So I am going to create a predicted matrix or an estimated matrix, and I'm going to call it the estimate. And the estimate is going to be equal to a substitution. And I'm going to substitute into L, all right, since we just found what L was. The variable for L was x2. And I have this matrix x1 of the predicted values, all right? So I'm going to substitute x1, and that's going to be our estimates, right? Now I'm going to do an fprintf or a for statement to print those out. So I'm going to say for I equals 1 to the length of x1, which is 4, we know, but in case it was ever larger, we don't have to count them. We're going to fprintf the estimate of L4, and let's just say percent 2.1f, since it's to one decimal place, is percent f, and we're going to do a new line, and we're going to print out x1i. All right, so that's going to print out each of the different x's right here into L4, and the estimate is going to be estimate I. All right, so this should take care of part B. So let's run it and see if we get an estimate. All right, and here's our estimates, all right, which look at least reasonable considering at 1.8 it's 0.5815, and right here it's 0.581 2. So we're pretty close to the values that are next to that. All right, so we're only a tenth off, a tenth off, a tenth off, and then down here we're off by not even a thousandth or anything, like maybe 1,000% or a couple of thousandths. All right, so at least it looks promising so far. All right, now I'm going to get an actual, and the actual is going to be equal to the actual Bessel J. So we have our function Bessel J of the first kind, which is the first parameter 1, and I'm going to substitute x1 into there. So now I have a matrix of actual values. And just to see what that matrix looks like, the actual values evaluated x1, we're hoping that the values look close to these. All right, so let's just run it to see what it looks like. And here's our actual value. So the actual value is 0.5812. The approximated is 0.581. If you round it, it's 2. So the estimate looks pretty good, 0.5683, 0.5683. So it looks like we've got a really solid estimate using our fourth degree polynomial. And of course, we should expect that using our Lagrange. All right, so for part C, we need a table to print out the errors. All right, and also the original value. So let's compute the percent error. So I'm going to say I'm going to do a for loop for this. So I'm going to say for I equals 1 colon length. In fact, we could just, well, I'll just go ahead and I'll compute it first. So for I equals 1 colon length of x1. We're going to say that error I is going to be equal to the absolute value of the actual, or the estimate, excuse me. So I'm going to say estimate of I, which is really our fourth degree polynomial evaluated at the given point. And then the actual of I, and then we're going to divide that by actual I and multiply that by 100. All right, so that's going to give us an error matrix. All right, so we have the estimate, we have the actual, we have the error. We're going to first print out what the estimate is, and now we're going to make a table. Okay, so now we're going to have an fprintf. So here's our header for the table. We're going to have the value of x. We are going to have the actual. So I'll just say j, j1 at, and I'm going to say %f. Well, I'll just say j1 at x. That'll work. And then we'll have L4 at x. And then we'll have our % error. I'm going to call it p error. If you put a % in there for some reason, it doesn't like it. All right. And let's just do one more for loop to print all of these out. All right, let me give myself a little bit more space. Right. And so we're going to say for I equals 1 colon length of x1, where we just do 4. We are going to fprintf. We are first going to print out the %f, and I will just say %.2.1f, since we know x is the 1 decimal place, and then we'll say %f. We'll say another %f, and then surprise, we'll say another %f. All right, and the parameters that we're calling are going to be x1i, which are the numbers all the way back up here that are in the matrix. Okay, that's the x value that we're estimating. J1 of x is going to be actual I. L4 is going to be the estimate I. And then finally, remember we had error. So error I. All right, so let's see what we get out of this. So we might have some spacing issues, hopefully no syntax issues. All right, the spacing was actually pretty close. All right, and this is the real gold that we're looking for. We're looking for these % errors. Now remember, these are not the error, these are the % errors. So it's not 6.29%, it's actually 0.062952%. That's pretty small, by the way, just making sure. So that's a really, really good percentage of estimate. Now I'm just going to do a space just because I'm obsessive compulsive about lining them up. Oh, I shouldn't have done that. I should have done the /n right here, just to put a little space in between the readout. There we go. And my % error is a little bit off, so of course I'm going to line it up. All right, there we go. So the moral of the story is this is a really, really good fit. All right. And of course, as we saw with the complexity of the Bessel function itself, I mean, just to compute one of these values would be pretty rigorous for us to do. However, we can interpolate them by knowing these values, right? So, and you can imagine if we had even more values, we could interpolate it a little bit more past 2.6 or behind 1.8. Right? The last thing we have to do is we have to go ahead and create some plots. And we're going to take a look at what the Bessel function looks like, but we're also going to plot it. All right, so this is kind of informing you guys a little bit about what Bessel 1 is, but then also to kind of get the idea of plotting this from the curve. All right, so let's go get to it. So I'm going to do a subplot, 1, 2, 1. And first of all, we need to plot the Bessel function itself. So I'm going to say y is going to be equal. Let's do this. Let's do an x3. I don't think we've used x3 yet. So let's say x3 is going to be equal to, and I think the range that we were asked to use was 1.8. Yep, 1.8 to 2.6. So we're going to say 1.8 in increments of 0.01 to 2.6. And we're going to say y3 is going to be equal to Bessel J1 comma x3. So we get our subplot. So now we're going to plot x3 comma y3. All right, so that's our plot. We're going to hold, and we're also going to plot the values that we got from the estimate. Okay, so that's going to be our y values versus what we had in x1. All right, so we're going to say x1 comma estimate, and we're going to put a dot on that. All right, and we're going to hold off, and let's just run this just to kind of see, and it might take a little bit because of the Bessel function, because it has to compute all of these numbers. So it's a whole bunch of numbers in there that it has to compute, like about what, 800 numbers. So it might take a moment. All right, so that's really cool. So check out how close these points are to the curve. All right, and notice it just gets a little bit further off each point we go away, and that's okay. It's not a big deal because it's still, error is really, really, really small. Okay. All right. Let's give it a title. So this is going to be our, so the title is going to be, let's just call it, let's say, Lagrange L4 interpolations plotted on graph of J1. X equals 1.8 to 2.6. All right. And our x-axis, we don't even need to label the axes, but we can say x label is going to be x values. And surprise, y label can be y-axis or y values. Or we could say Bessel values if we wanted to. All right, so that's pretty cool. And the good news is that we can just copy this. And I think the other part of the problem was to change it to 0 to 30 to kind of get a holistic view as to what the Bessel function looks like. So here's our subplot, and this is going to be J1 from 0 to 30. All right, so I think that's good. Let's go ahead, plot it one more time. All right, so for those of you that have never seen the Bessel function plotted, not surprisingly, it kind of looks like a little bit like a trigonometric function, all right? And it's going to have like these oscillatory sorts of behaviors, and it damps, but it doesn't really completely damp, unlike, you know, other damp sort of functions, like when it's e to the minus x sine x or something like that, where it eventually converges to 0. Here's our points on the curve, which show us at the beginning we have a really good interpolation for those values. Of course, the further we go away from that, the less likely this is to be a good interpolation. And then here's kind of the zoom. All right, so this is the bigger picture of the zoom. Just to play around with this, we could change this to 100 to kind of get a bigger view as to what the Bessel function looks like, or a longer view. All right, so, and again, that oscillatory behavior continues, and then we could even do it for 1,000 if we really wanted to. So at this point, I'm just playing around with the Bessel function, but it's kind of cool, at least to me. And so yeah, that's pretty cool. I don't know if it'll do 10,000 or if it'll break. Let's see. Nope. All right, so sorry about that. It still has those plots at the very beginning. So actually really cool how our Bessel function kind of levels off at this point. So you could probably find what the limiting behavior is of Bessel as it approaches infinity, which could be done probably in, you know, some sort of advanced calculus class or something like that. But anyway, we've done what we need to do. Pretty cool. We've explored the Bessel function just a little bit, but also we've explored the Lagrange interpolation at a high level. So hopefully this helps you to understand the use of Lagrange as well as the Newton interpolating polynomials, um, and how they can be really useful to find those values in between other given values.